Hello, good morning. How are you? Do you hear me? Do you hear me? Okay, want to know whether you hear me or not? Okay, I hope it's clear. All right, let's we continue our class. All right. Okay, you will say that, for example, Purani said that, wow, we don't have time to finish chapter 8 on boundary value theorem and initial value problem. So how I can go to chapter 9? Come on, not all the question come out, just a specific question, but you need to know the all topics overall, right? So to make sure that you can earn your marks. Okay, how many percent just now? All right, I just write here is around 50% for chapter 7, chapter 8, chapter 9. It's almost three big questions. Means that one question you need to spend how many minutes? 20 minutes. So you have a skill to do a discussion using chapter 5. This is not a new, but there is a combination from the chapter 5, and then how you use the chapter 4, a Taylor series, and then how you find the boundary discretization to fix into the linear system, and then you solve a linear system using Thomas in chapter 2. All right, so this is only a combination which is you are quite expert, all right, on this chapter 5, chapter 2, chapter 4. Just to write, just to write the discretization of boundary value problem, all right, and then solving a direct method using initial value problem based on the Euler, Taylor, and Rajkata. All right, okay, don't feel this is very difficult chapters. All right, if you have a problem, let's WhatsApp or Telegram. All right. Okay. Good morning, Mas. Good morning, Salwa. Good morning, Purani. Good morning, Amelia. All right, Amelia. Good morning. Okay, and then who's here? Okay, if I'm not pronounce your names, I'm sorry because we want to go to the chapters. All right. Okay, now we go to do some revision. So the objective I meet you today is to do a revision for chapter 8. And then I want to explain on partial differential equation in chapter 9. All right. Okay, because we are doing same style. Okay, for solving partial differential equation similar to boundary value problem. We're still using chapter 5 on discretizing second order derivative or first order derivative. All right. Okay. Come on, let's we continue. Okay, I hope I can share with you the PDF file. Okay, where is my PDF file? Come on, I share with you the PDF file. Go to the PDF file. All right. Okay. You have this note. Because if you go to the e-learning, I just present you the e-learning just now. I go out. I want to focus on these notes. Okay, this is my video, but I write the way I write. I put it in the PDF file. All right. So now let's reconsider to let's refocus to this PDF file. All right, in the PDF file, okay, I make it more bigger. I zoom, all right, zoom to, let's say 120%. All right, so now you learn already three methods, all right, which is the powerful is a Rajkata with a second order, and then the complex is a Taylor series with the second order. You need to derive the formula. And then Euler is simplest one because Euler is a Taylor series order 1, all right? And then we solve already the boundary value problem using three types. Okay, I want you to focus on the derivative at the corners. Okay, x equal to b or x equal to a, all right? Okay, derivative for both corners and without derivative, I think this is too complex, and then without derivative is too simple, all right? Because we want to create matrix 5 times 5. All right, The initial value problem, okay, is okay, how we, in this case, you need to set in your mind your fxy is a dy over the x. All right, what is a fxy? Is a first derivative y respect to x. So this is your aims, and then you need to modify this function to make a second derivative or third derivative based on the order. All right, what is your function? Your function is to find the value of y. In this case, y is a temperature, behavior, the velocity, okay, maybe the dimension, all right, the region, we don't know, okay. This is direction of chemical. So y is a function that you want to find, and x is a domain, whether x is maybe time, maybe okay, maybe the range, okay, the dimension is on. So this is your focus to find y. So the easy is using only two terms using Euler method. All right, and then okay, and then you learn, okay, okay, to find the error, you have to know, okay, two types of grid. The first is Euler that you generate to get y naught, y1, y2, y3, y4, y5, for example, and yi from the exact solution. So you will get the approximation, you can get the error, absolute error. And then the absolute error, we can ask you what is a summation error to compare between the method, for example, right? For example, we always compare with the Taylor series, all right? Taylor series, okay, in Taylor series, you can see here is a very complex, okay, complex, the way how you write is a, okay, first order, second order derivative, third order derivative, and fourth order derivative up to k plus 1. K is an order. So you can derive Taylor series in the order 2, order 3, or order 1. Order 1 is a Taylor, order 2 is a Taylor's method, order 2, and order 3 is a Taylor method, order 3. Because Taylor method is a long process of the calculation, we make it simple using range kata. It depends on step. So we will put in the 2 step, all right, which is K1 and K2, or 3 step or 4 steps, okay, which is K1, K2, K3. All right, so it depends on step because the Taylor's is too long, the calculation is too long, all right. So now we can solve this problem using Taylor's or range kata. All right, come on, when you said that you want to solve using Taylor, all right, what should you need to do? What should you need to do? You need to remember the formula. All right, the same style. You need to draw the graph y1, y2, y3, y4. All right, don't forget what is n. N is a number of sub-interval, number of grid is a b minus a divided by h. Okay, the grid involved is a b minus a divided by h. H is a size of interval. B is the last corner of the boundary. A is the first corner of the boundary. You have to know. All right, from the question, okay, you can also know what is I when I equal to 0, what is a x naught, what is a y naught, because x naught is generated from h. You know that y naught is a given in the question, okay, to start the iteration, all right. So in this case, y naught is given by 1, so you can create y1, all right. And then to create y1, you need to know y naught prime, y naught prime prime, y naught prime prime prime, if this one is a Taylor series order 3. All right, so this one, okay, in this process, don't make it simple, okay, because they will give you a marks, all right. Since you have 3 expression to find, okay, be careful. Put the value of x naught, put the value y naught carefully, because this is an independent, it's a dependent. So you will get y1, and then you increase to I equal to 1, all right. You will get y2. When I equal to 2, you will get y3. When I equal to 3, you get y4. This is a direct method. Direct. It's not involve iterative. It's not involve a matrix, but it's involved to draw a line for y0, y1, y2, y3, y5. All right. For range kata, all right, range kata, okay, we are very simple because we need to find K1, K2. All right, there are two types of the range kata. Range kata, you have a hand method and midpoint method. Use hand method, okay, focus on hand method, all right? Okay, so now this is a time for you to increase your calculation, okay, your discretization. This is very important, yeah? Okay, to know about boundary value problem, we have 4 conditions, but focus on the 2 conditions. Condition at the corners, okay, at the x equal to a, and then derivative x equal to b. The way you derive will be more explained in chapter 9. In chapter 9, because we're still using chapter 4, 5.8 for the first order derivative using center, using 2 point, fi plus 1 minus fi minus 1 divided by 2h, and then for the second derivative we have a 3 point, fi plus 1 minus 2 fi plus fi minus 1 divided by h squared. All right, f is 1. All right, so set in your mind. All right, I hope all at your fingers, because we need to write in 20 minutes. All right, in 20 minutes. All right, okay, now, okay, anybody fine? Okay, fine. Okay, everybody fine? So I hope, okay, this is time for you, okay, to focus and then go to the let's we go to the exercise here. All right, I'm stop sharing. I want to go to this. Okay, I want to go to this. All right, so now since you are work in group, please, when you work in group, please, okay, there is a few questions here. Divide into the group, right? Divide into the group. And then, okay, okay, since I put in here, in the interface like this, very easy everybody to find the answer. So this is a skill I need to be improved for chapter 8. All right, please. This is a skill that you need to improve for chapter 7 and chapter 8. Chapter 7 is very easy, just to find what is lambda 1, what is a lambda 3, what is lambda 2. All right, using the Gauss-Green theorem to find the lambda area. Okay, power method to find the dominant eigenvalue and or maximum eigenvalue, and then shifted power method to get the minimum eigenvalue using matrix B. B is equal to A minus lambda 1i. All right, and then find the other eigenvalue, which is lambda 2. So you need to know 3 formula: power method, shifted power method, and how to find lambda 2. All right. Okay, so okay, from this exercise, I'm also request you to use Taylor series order 2, range kata order 2, all right, Euler order 1, to solve the initial value theorem, initial value problem, and then please remember the boundary, the initial, how you use initial in your equation. All right, so now, I'm stop sharing. I want to go, all right. So now I want to go to this material, all right. Even though you have to know we are using, streaming, you can, watch this movie. All right, this is a movie. Somebody said that, Purani said that this is not a movie. This is the knowledge sharing is depend on you, because all at the YouTube, very easy to catch, very easy to see, very easy, for example, to you with your low bandwidth, you can go to the YouTube. All right, any problem, let me know, contact one-to-one tuition. All right. Okay, now let's go to the sharing, stop sharing. We go to this introduction to partial diffusion equation. I love this subject. Come on. why I love this subject? Because, okay, this is my basic PhD. This is my basic PhD. All right. Okay, Purani, you know that this is my basic PhD. You can ask me a complex question about this topic. All right. You can ask me about the big data based on this subject. You can request me how to solve a simulation using a big data of this topic, chapter 9. I can answer the question and I love to get the answer from you. All right. So now let's refocus. All right. We focus our video now. Okay. What is a partial differential equation? All right. So I start my subject by comparing between ordinary differential equation in chapter 8 and partial differential equation in chapter 9. All right, in chapter 9, we are using many parameters. For example, x, y, and t. Domain, x, y, and t is the temperature. But for ODE, ordinary differential equation, y is only depends on x. It's only one variable. It's only one variable. So now let's solve the partial differential equation. The process similar to ordinary differential equation because the first strategy, we need to determine the domain. We need to find the x0, x1, x2, y, x2, x3, xn. All right, y0, y1, y2, y3, y4, and yn. And then, as usual, we need to do a discretization of partial differential equation, okay, using chapter 5, 5.8, and 5.11. All right. Generate the grid. Okay, generate the grid. You are creating a linear system of the PDE and ODE based on the finite different method from chapter 5. All right. And then number 4, consider the initial and boundary condition. All right. All right, you have an initial and boundary condition. You use this value inside, put inside when you do a generation of the grid, when you do a generating of the grid. All right, now you are develop a linear system. This is the time for you to solve a linear system using Thomas as a direct method or Jacobi or Gauss-Seidel as a iterative method. All right. And then you will get what? You will get the set of Uij. Uij is what? U, Xi, Yj, and Tk. Okay, because it's depend on time. Okay, it's depend on the region, the dimension. The dimension is a 2 here, X and Y, and T is a time. All right. So the process of ODE and PDE almost similar in terms of the discretization. Number 2, generate the UI. Number 3, consider the initial or boundary value to insert to the linear system. Number 4, and solve the linear system. If the question not ask you to solve a linear system, you don't need to solve. You leave it the matrix, okay, AU equal to F as the ending of your solution. All right, so now I write here, okay, I write a standard form of the partial differential equation. What is that? A del squared U over dx squared, B del squared U over dxy, plus C dx squared U over dy squared, plus D del squared U over dx, plus E del U over del y, and then plus Fu equal to G. So this is a standard, the standard of the PDE. All right, so we are not focused on the parameter B. B is equal to 0. All right, we are not focused on D. D is equal to 0. We are not focused on E. E is equal to 0. And F equal to 0. So you are very lucky because all the B, C, D, B, D, E, F is 0. All right, so you just have what? You just have A, okay, del U over del x squared plus del U over del y squared. All right, and then maybe you have Fu equal to G. All right, so this one is a standard form that you get, and we can categorize this standard form into three categories. The first is, okay, parabolic. The second is elliptic. The third is a hyperbolic. So we are not asking you all the question. We just find which is going to come out, whether parabolic or Poisson or hyperbolic. All right. So not all we are going to ask you to solve the problem, because the process is very long. 1 to 6. 1 to 6. You need to solve in 20 minutes. All right. So now, okay, here. This is the way how we write. Okay, in the partial, you need to have a delta. Delta is not is different with the ODE. Delta is a curve there. All right. And then these types, the first is the elliptic, parabolic, and hyperbolic. What is elliptic? Elliptic when b squared minus 4ac less than 0. All right. What is the elliptic? Come on, we go to the elliptic. B squared minus 4ac equal to 0. What is a b? B is a coefficient for d squared over dx dy. All right. What is the parabolic? When b squared minus 4ac is equal to 0. And what is hyperbolic? Hyperbolic is a b squared minus 4ac greater than 0. All right. So the question will come one of this category. All right. One of this category. I write here, okay, the elliptic, okay, if you put A is equal to 1 and then the C is equal to 1, this is a way how you write elliptic. Del squared u over del s squared plus del squared u over del y squared equal to uxy. Alright, this is a Poisson elliptic with the Poisson type. And then this is a parabolic, del u over del t equal to del squared u over del x del y squared. Alright, means that your, come on, we go here, means that your C is equal to 1 and then your D is equal to 1. Alright, the rest is a 0. Alright, and then hyperbolic, del squared u over del x squared minus del squared u over del y squared equal to 0. Alright, so hyperbolic is a minus. You have minus or equal to y uxy. So hyperbolic is what? There is a minus here. Alright, when you put equal on your right hand side, there is a minus here. This is a hyperbolic. Alright, what is an example of this application? Come on, I want to ask you, why we need to learn parabolic? That is a question. Why we need to learn partial differential equation? What is we need to learn partial differential equation? We need to learn partial differential equation because almost the application, okay, in the world right now, for example, the temperature behavior, the rainfall, the increasing of the flood, okay, in our area, raining almost every day, all right, and then the temperature behavior of the device, for example, whatever, okay, the printed circuit board of my computer is heating. All right. So in this case, the heat, the diffusion temperature, the temperature behavior is depend on the device itself. All right. The space, the time. All right. All right. And then the room temperature, the aircon, the fan moving. All right. Okay. So this is many variables involved. There are so many variables involved to predict the temperature behavior for a certain application. That's why we need partial differential equation. All right. For example, the tumor growth, the cell growth, the brain tumor growth, all we can represent the partial differential equation respect to time and space, respect to volume, respect to the region, respect to the velocity, okay, mass, okay, and then diffusion of the growth. All right. So that's why this is very important. Right, this is very important. Now let's refocus to our subject. All right, we don't want to focus on so much. Okay, we want to. All right, we go to this. All right, so now, Okay, we know already what is a three category. So the first category that I want to focus here is elliptic. Okay, don't say that when I focus elliptic, okay, there is a difference with the parabolic and hyperbolic. No, it's similar. Just okay, elliptic is a del square u over del y squared plus hyperbolic del square u over del x squared minus parabolic. One is a first derivative, the other one is a second derivative. So all is applying chapter 5. 5.8 is a first order derivative and second order derivative and first order derivative. All right. The important here, you know that, okay, when I say uxy, you can write as a uxi yj equal to uij. This is I teach already to you in chapter 5 how to make the simplest way of writing. All right. So now, all right. Okay, the simplest way of writing. All right. So now let's go to the one type of parabolic equation we call as a Poisson equation. What's that? It's a Poisson equation. Okay, come on. I told you u is depend on x and y. So you write u I y j. Y is a x, y axis. X is a dimension at x axis. Okay, x exponent y is not involved any derivative. You just put xi exponent yj. All right. Okay, I draw already the graph. And then there is a boundary condition. There is a condition here. X between 0 and 1. And the temperature is between 0 and 1. Okay, the dimension is between 0 and 2. And then the temperature y is between 0 and 1. So you know that is given in the question. Let's go. Come on. Go to your books. Where is your notes? Okay. I can share already the notes with you. Go to the books, okay. Go to the chapter. Where is my chapter? Yeah. Okay. I go to the chapter 9. Okay. Go to the books. All right. Where is your book? Chapter 9. PDF file. All right. Go to the PDF file. Where is the chapter 9? Come on. Okay, chapter 9, let's go to the boundary elliptic equation. Okay, I'm using example for 9.1. I'm using example 9.1 page. You go to page 234. Come on, go to that book because it's very easy for you to go to you can watch how the discussion, okay? All right, at the same time, you can hear my class, all right? So now, let's focus. Okay, we focus our class now. All right. Okay, all right. Okay, now, okay. Okay, we have two types of the. Okay, we have two types of the parabolic. The first is a Poisson, and then the second is a Laplace. But most of the question based on Poisson, Laplace, because Laplace is not equal to 0. But some question we focus on Poisson. Poisson is equal to 0. All right. I think it's Poisson, I think is, come on, we go to the, all right, come on, we go to the Poisson equation, boundary value problem, Poisson equation, okay. Laplace is equal to 0 and Poisson is not equal to 0. I'm sorry, yeah, Poisson is not equal to 0, Laplace equal to 0. You can see the correct in my notes. All right, so there are two types of Laplace. Okay, we are elliptic. We have Poisson. Okay, d squared u over del squared plus del squared over del squared is not equal to 0. Okay, the other is a parabolic equation. Okay, we can solve parabolic equation. What is the equation for parabolic? is a del u over del x or del t equal to del squared u over del y squared, right? So we can use parabolic to find the temperature behavior, diffusion equation, right, for the temperature and so on. All right, so there are three types to solve: explicit, implicit, and constant. I'm using theta to make it different. All right, and hyperbolic is opposite of elliptic. Okay, one of the notation should be negative. Okay, del squared u over del x squared minus del squared u over del y squared, for example. That's a hyperbolic. All right, so you can see the pattern is similar. Okay, the pattern is similar, but okay, the solution is depend on the initial and boundary condition, right? And then the way how we do discretization is similar using chapter 5, okay, 5.8 and 5.11, right? So the the application of a wave equation and elliptic equation is a wave, for example, the sound, okay, the movement of the sea, all right, the wave from the water, the air, okay, the signal, and so on. So that's why we learn hyperbolic, because it depends on the wave. Depends on the wave. All right. So now, let's we go to the application. Okay, parabolic for temperature behavior, the tumor growth, for example. Parabolic is the wave, elliptic is the wave, for example, the wave of the wind blow, the water wave, the the macro, and then the signal, and so on. So we need to know three types of the parabolic. What is that? Elliptic, parabolic, and hyperbolic. Okay, the way how to discretize almost the same, but there is some condition which is we need to change at the boundary, okay, at the early boundary and the last boundary, okay, because there is an initial and boundary condition. Yeah, because there is a initial and boundary condition. All right. So now, I hope okay, you can understand. Okay, let's we go to the okay, for the next one. Okay, let's we find this one. All right, let's we concentrate on the chapter 5. Okay, let's we concentrate on chapter 5. All right, the question here is how we want to discretize, okay, the problem. How we want to discretize the problem, how we want to find the boundary value problem and put in the equation. So that is I want to teach you, because you need to be careful, because the boundary is a 4. There is 4 boundary. X equal to 0, x equal to n, y equal to 0, y equal to n. So you have how many boundary? 4 boundaries. So be careful. All right. So your answer is inside the boundary. The inside in the region. All right. So parabolic equation mostly is 2-dimensional. Ordinary differential equation, you just draw a graph, but here you draw a space x and y. All right. Okay. Now let's we continue. Okay. All right. Where is my is here, but here. All right. Maybe I need to focus here. I want to focus this one. Let's stop sharing. All right, I go to this. Okay. All right. So now, all right. I hope I go. Yes, I'm going to this. Okay. All right. So now, okay. This is a question that I want to focus. Okay. This is a Poisson equation. It's not equal to 0. It's not equal to 0. And then this where if we equal to 0, okay, x exponent y is equal to 0. So this will be Laplace. Okay, will be Laplace. All right, let's be focus. Okay, and then we know that there is 4 boundary here. X equal to 0 to 2, y equal to 0 to 1. All right. So with the boundary condition, okay, this is only a space. Okay, the dimension. The boundary condition is when x equal to 0, y x naught yi is equal to 0. This is the way how I write, yeah. When x equal to n, y xn yj is equal to 2 exponent j, right? And then the other side is when y equal to 0. Where is y equal to 0? Is somewhere here. Okay, y equal to 0. All right, and y equal to 1. Okay, the value of y xi y not equal to xi. All right, when y equal to m, so you can get u xi ym equal to xi exponent. All right, so where is the location of this boundary? So this equation, because now you have how many boundary? 4 boundary, all right, with the x between 0 and 2, y is between 0 and 1. Okay, so before this, you are learn boundary value problem. There is only one boundary, all right, between x0 and m, all right. Now, we want to solve, okay, this problem using linear system of equation, right? And then we want to solve using, not Thomas, I want to use using iterative method, we call Gauss-Seidel method, with the initial and boundary condition, right? So this is, I want to solve this linear system, okay? And then, all right, since we have a 5 step just now, what is the step? The first is find what is a m and n. Since your delta x and delta y is equal to 0.5, so your n is similar. N is a b minus a divided by 0.5 is 4, and m is a b minus a divided by y. Okay, let's we go to the b. B is 1 minus 0 divided by 0.5 is equal to 2. All right, so okay, when I give you the dimension, okay, the region for x and y as is, be careful. You have n, maximum point for x n, and m is a number of grid for y m. Okay, the maximum point for y and x. The maximum point is a y2. The maximum point for x is x4. All right, x4. This is a grid. Okay, not a value. It's a grid, the location of the grid. So you derive where is x1, where is x2, where is x3, where is x4, where is y1, where is y2, where is x0, where is y0, and then draw the line. Okay, come on. Okay, this is a very important step. Okay, where is your domain? Domain now is a 2-dimensional, not like boundary value problem. You have 1-dimensional. You only have a draw a graph, but here you draw a space. All right, so you draw and then you make it in the net like this. Okay, so when you get a net like this, you can get what is the point x1, y1. Where is the point x1, y2? Then where is the point x2, y1? Where is the point x3, y1? Where is the point x4, y2? All right, so now here you be careful. Student always cannot understand the way how I write. You have 4 boundary. When x equal to 0, I said u0j. Okay, where it's come? It's come from your boundary condition. Where is your boundary condition? Is here. Where is your boundary condition? At the question. Why? Okay, when u is equal to 0, when x equal to 0. U is equal to 2 exponent y when x equal to 2, the last point. And then u is a temperature, yeah? Y is a dimension at y axis. X is what? X is a dimension with domain at x axis. So y is equal to 0 when when u is equal to xi. And then y is equal to 1, y is equal to m when u is equal to xi exponent. Be careful. I is a location. U is a value. Y is a value. I and J is a location. All right, be careful, yeah. Don't mistake the comparison, the difference between I, J, X, and Y. All right. Y is a value, X is a value, I, J is a location of the domain. All right. So now it's not like boundary value problem. Initial partial differential equation, you need to draw the point. Where is the point? The last point when x equal to 0, and then x equal to x I equal to 4, x4. When y naught and y2. So there is a boundary. There is a corners of your space. Right? So in this case, you transform whatever I said just now, the four boundary, to the grid point. This one you need to expert. You need to improve your skill. The way how you write from the question to the grid. All right, I give you a question. Now you write U0J is equal to 0. Where is the line? Number 1, when x equal to 0, the y axis. Number 2 is when x equal to n, okay, I is equal to n at U4J, the last point of the y-axis. Number 3 is when y is equal to 0, all right? I is equal to 0 is the x-axis. And then the last point when j is equal to 2 is a y2, all right? Here is a y2, all right? The last, okay, axis of the last domain of the y-axis. All right, so this one you need to be careful, yeah, because I give already the value of y is between 0 and 1. I give already the value of x is between 0 and 2. All right, so just add in je. You just learn from the boundary value problem. Now we just add in because your dimension is 2 by 2. Don't feel this is a problem. So where is number 1? Number 1 is here, the line here between okay, the y-axis. There are 3 points here: x0, y0, x0, y1, x0, y2. Where is number 2? When I equal to n, when I equal to 4, is x4, y0, x4, y1, and x4, y2. Where is number 3? Number 3, when y is equal to 0, is below. Number 3 is x0, y0, x1, y0, x2, y0, x3, y0, x4, y0. Where is number 4? Number 4 is when y2, all right? Meaning that x0, y2, x0, x1, y2, x2, y2, x3, y2, x4, y2. All right, so I repeat again where is the line? Okay, now my question, how to find the grid at x1, y1, x2, y1, x3, y1. All right, the 3 point inside the corners. Okay, the 3 point inside the region, the 3 point of the boundary. Where is the point there? x1, y1, x2, y1, x3, y1. All right. Okay, now let's be focused. Okay. Now, can you extend the dimension from one-dimensional to two-dimensional? All right. From dimensional, okay, dimension that you learn from the boundary, from the boundary value problem to two-dimensional. Okay, before this, we just focus x axis, but now there is a y. When you have a y, you have a space to get the value of the x1, y1, x2, y2, y1, x3, y1. Okay, the rest is a boundary. The rest is have their own value. There is a value. Where is the value? At the boundary. Be careful. All right, be careful. This is my question. Can you, okay, investigate, put the value at the boundary for the two-dimensional problem? All right, for the two-dimensional problem. So that is our problem. Okay, now let's be focused to the next step. The next step, okay, this is the first step. Yeah, this is only a first step. All right. So now let's go to the next step. Okay, go to the next step. All right. All right. I go to the next step. Okay, I'm stop sharing. I go to the next step. How to, let's I go, if I can go, how to, okay, discretize the partial differential equation. Okay, it's not here. Come on, it should be here. Alright, so I go to the slide, okay, for the next one. Where is this one? Okay, what is how to solve? Wait, okay, I can solve here. Okay, this one is introduction, how to discretize. Alright, we already have here. Alright, we know already the point. Okay, and then now we go to the discretization. Right, we go to the discretization. Right, so now I will stop sharing. I go to the how to discretize 164. Alright, so now I hope I can share with you. Okay, let's we continue to the how we do the process of discretization. Alright, so just now I repeat again. Okay, I repeat again how you declare how you fix the value. For example, here you want to find u00. U00 will be 0. Alright, u40 will be 2 exponent y0. Alright, so means that you need to find the value. Alright, now you want to find u20. U20 is here, is x2. X2 is a 1.0, right? 1.0. You just fit in the value, right? Don't worry. Don't worry, but you need to aware about there is all the value at the corners. There is a numbers. Okay, just you need to find the three value inside the region, inside the boundary, right? So now, okay, since you know all the question, you transform to the graph, means that you get the extra marks. The second step is let's we go for the discretization. Okay, how to do the discretization. Right, when we do the discretization, you need to focus on the chapter 5. Okay, chapter 5. Go to chapter 5. We want to discretize elliptic equation using finite different method 5.8 and 5.11. All right. Your question is a uxx plus uyy equal to exponent ey. I transform to the second order derivative respect to x and respect to y. I apply the second order derivative respect to x. Okay. So what I do here, I'm using 5.11. Okay, chapter 5. You go to 5.11. Okay, from here you can see I do a second order derivative using 5.11. It's a ui minus 1 because this one is a derivative respect to x. So I change I minus 1, I and I plus 1 divided by h squared. All right. So now I want to apply the formula 5.11 respect to y. So I focus j, all right, because y is j. So uj plus 1 minus 1 minus 2 uj plus uj minus 1, all right, divided by delta y or k. I just put k, all right, because to make it different with the h. Sometimes j is equal, delta h is equal to k, all right, sometimes. And then plus xi exponent yj. So this is a discretization that I'm doing. I just apply chapter 5 for two types of discretization. And then next I put I, okay, I maintain I on the second terms and then I put j at the first term. You can see that my point now is depend on the two grid. Just now I changed the I because derivative respect to I, right? And then I change okay, derivative respect to y, I change j, and now I put, okay, the value of j for the first term, and then the value of I, okay, the I notation for the second term. So you can see here it looks like complex, but I start with the derivative respect to x, derivative respect to y, and then I just put the grid inside the equation. This will be your star. This will be your star, all right? Since delta x and delta y is equal, so means that h and k is equal, so you times delta x every both part. This is a common, okay, this is a common way because, okay, we want to find lambda. Lambda is a delta x over delta y, all right? So we put one lambda, okay, one parameter to make it more clear, right? So you can get lambda square uij minus 1 minus 2 uij plus uij plus 1 equal to h squared xi exponent yj. All right. So, okay, we hope that lambda is equal to 1 because delta x given in the question and delta y is equal to 0.5 or similar. So you derive in simple way, you can get ui plus 1j, all right, minus 2 for uij plus ui minus 1j, all right, and then plus ui minus 1j. Okay, you derive the same. How many notation you have now? 3 plus 3 is a 6 notation, but you make it 5, all right, you make it 5 because uij here and uij here you can plus, you can get 4ij. So what you create now is only 5 point. Where is the 5 point? Okay, the first point is a ui minus 1j. The second point is a uij. The third point is a ui minus 1j. And then fourth point is a uij minus 1. And then the last one is a uij plus 1. So you have 5 points, right? 5 points. Okay, because your derivative is respect to x and respect to y, and then because uij is a center point can be combined to 4 uij, so you can create 4 points. We call this one is a 5-point discretization, right? 5-point discretization. So till here, you are success to convert the elliptic equation to the elliptic discretization based on 5-point discretization computational molecule. Sometimes we call it as a computational molecule, right? So this is like your model, your design, your pattern to be solved any point at the graph that I draw just now. This is a basic point that we are going to apply 5 discretization to find the value, right? So now we have what you create now is a 5 point, right? In the boundary value theorem, you create how many points? 3 points. That's why your matrix is 5 times 5. The diagonal is a 3 diagonal, okay, equation. But here you have 5 points. Ui minus 1, again, ui minus 1j, uij, all right, and then ui minus ui plus 1j, uij minus 1, and ui j plus 1. All right, so you have 5 points. So please correct this one is a ui plus 1j. Yeah, all right, so you have 5 points. Right. So now my question, okay, I'm stop here. All right, my question here, you already, okay, you already transform, okay, or discretize, we call it as a discretize elliptic, okay, elliptic equation to how many point? To 5 point. Okay, to 5 point computational molecule. Okay, to 5 point computational molecule. All right, so you keep this molecule. Why? Because you want to solve this problem. Okay, in generating the grid. Okay, the grid. Where is the grid? The grid is when x equal to 1, y equal to 1, x equal to 2, y equal to 1, okay, j is equal to 1, and then I is equal to 3, and j is equal to 1 at the center of the region. All right, at the center of the region. So now my intention now, until now, you know how to convert the boundary and initial value problem to the discretization form, and then you already know how to convert elliptic equation to the 5-point discretization form. Right? Okay. Before this, you are using 3-point in the boundary, but now you are using 5-point again. Okay, I just want to make you understand. All right, so now the next stage is how to generate the grid, okay, the solution. How to generate the solution. That's our problem now. You see how to generate the solution. Right? Come on.